Welcome to Homework Lib.
Question.
Capacitor network analysis, equivalent capacitance, charge, and voltage. To solve the problem, we need to determine three things. 1. The equivalent capacitance of the network. 2. The charge on each capacitor. 3. The voltage across each capacitor. This process involves understanding and applying the concepts of series and parallel combinations of capacitors. Let's walk through each step with thorough explanation and mathematical rigor. Step 1. Calculating equivalent capacitance in series. We start by analyzing the given circuit. It has combinations of capacitors in both series and parallel. Combination 1. Series combination capacitors in series are combined using the reciprocal formula. Frac 1 C text EQ equals frac 1 C1 plus frac 1 C2 plus C dots. Let's apply this formula to calculate two subunits from the top image. First group in series. C1 equals 652 mu F. 6 mu F capacitor in series with C1. Frac 1 Cx equals frac 1, 6.52. 6. Right arrow Cx equals 3.125 mu F. Second group in series. C2 equals 8.54 mu F. 2 mu F capacitor in series with C2. Frac 1 Cy equals frac 1, 8.54. Plus frac arrow Cy equals 1.62. Step 2. Combining in parallel. Now, Cx and Cy are in parallel. For parallel combinations, capacitances simply add. C text equals Cx plus Cy equals 3.125 plus 1.62 equals 4.745. So the equivalent capacitance of the network is boxed C text equals 4.745 mF. Step 3. Calculating total charge in the system. The total voltage provided is V equals 90 volts. Using the formula for charge, Q equals C, substituting the values. Qt equals 4.745, F dot 90 volts equals 4.275 times 10 to the minus 4, C. Step 4. Charge and voltage on parallel capacitors. Since Cx and Cy are in parallel, they experience the same voltage. Vx equals Vy equals 90 volt. Charge on Cx. Qx equals Cx dot Vx equals 3.125, F dot 90V equals 2.815 times 10 to the 10 minus C. Charge on Cy. Qy equals Cy dot Vy 1.62 mu F dot 90V equals 1.458 times 10 to the 10 4 C. So far we have Qx equals 2.8125 times 10 to the minus 4 C. Qy equals 1.458 10 to the minus 4 C. Step 5. Analyzing series capacitors. Breakdown of Cx. This is a series combination of 6.22 mu F, denote as C1. In series, the charge is the same across both. QC1 equals Q6 mu F equals Qx equals 2.815 or C. Using the formula V equals frac QC, voltage across C1. V1 equals frac Qx 6.52 mu F. We'll frac 2.8125 times 10 to the minus 4, 6.52 times 10 6 equals 43.14 volts. Voltage across 6 mu F capacitor. V6 mu F will frac 2.8125 10 to the minus 6, 10 6, 46.87 volts. Check. Total voltage equals V1 plus V6 mu F equals 43.14 plus 46.87 to 90.01 volts. Rounded approximation is acceptable. Breakdown of Cy. This is a series combination of C2 equals 8.54 mu F, 2 mu F. Both capacitors have the same charge. QC2 equals 2 mu F, Qy equals 1.458 times 10 to the minus 4 C. Voltage across C2. V C2 equals a frac 1.4558 times 10 to the times 10 minus 6 equals 17.1 volts. Voltage across 2 mu F. Capacitor. V2 mu F equals frac 1.458 times 10 to the minus 4, 2 times 10 minus 6 equals 72.9 volts. Check. Total voltage equals 17.1 plus 72.9 equals 90 volts. Final results summary. After completing all calculations, we summarize the results. A. Equivalent capacitance equals 4.745 Vi mu F. Sharp B. Charge on each capacitor. Capacitor, charge, Q coulombs. C1 equals 6.512 mu F. 2.8125 times 10 to the minus CF. 2.8124 C. C2 equals 8.54 F. 1.458 times 10 to minus 4 C. 2.458 times 10 to minus 4 C. Thermal voltage across each capacitor. Capacitor, voltage V. Volts, C. C1 equals 6.552 mu F. 6, 46.87 V. C2 equals 8.54 pacidences. 722.9. Conceptual understanding. Capacitors in series. Charge remains the same across each capacitor. Voltage divides depending on individual capacitances. The equivalent capacitance is less than the smallest capacitor in the series. Capacitors in parallel. Voltage remains the same across all capacitors. Charge divides in proportion to capacitance. The equivalent capacitance is the sum of the individual capacitances. Physics insight. In real circuits, combining capacitors allows us to adjust time constants in RC circuits, filter signals in AC circuits, and store electrical energy. This problem reinforces the theoretical understanding and shows how different configurations impact system behavior in terms of energy storage, voltage distribution, and charge accumulation. Series combination is often used when higher voltage tolerance is needed. Parallel combination is used when higher capacitance is needed. Conclusion. We followed a structured approach to solve a combination of series and parallel capacitors. 1. Reduced series capacitors to single equivalent units. 2. Combined the equivalents in parallel. 3. Used the total voltage to compute total charge. 4. Broke down equivalent capacitors back to components to find individual voltages and charges. 5. Applied basic capacitor formulas Q equals CV, frac Q, C. By applying foundational concepts and equations consistently, we accurately determined all the required values. Equivalent capacitance, 4.745, meant charges on all capacitors, ranging from 1.458 times 10 to the minus C to 2.8125 times 10 to minus 4 C. Voltages across each capacitor, ranging from 17.1 volts to 72.9 volts.